Have you ever wondered why some of the world's most advanced robots look strangely familiar? From cheetah-like robots sprinting at incredible speeds to drones that flap their wings like insects and soft robotic arms that move with the fluidity of octopus tentacles, today's machines increasingly borrow ideas directly from nature. In this video, we explore the world of bio-inspired robotics, where millions of years of natural evolution are translated into engineering breakthroughs. This is Design Hub Heavy Machinery, and today we unlock nature's engineering secrets. Nature is essentially the world's longest-running research and development laboratory. Every organism, whether an insect, a mammal, or a marine creature, has evolved structures and control mechanisms that maximize energy efficiency, agility, and adaptability to harsh environments. While traditional robots rely on rigid structures, electric motors, and predictable programming, nature shows us designs that are far more optimized. Animals move with minimal energy. Birds change wing shapes effortlessly for flight control. Insects detect motion almost instantly. These natural abilities inspire engineers to rethink how machines should be built. Bio-inspired robotics is not about copying biological shapes. It is about understanding biological principles and translating them into mechanical, structural, and algorithmic innovations. One of the clearest examples of nature-inspired engineering appears in legged robotics. Consider the cheetah, nature's master of dynamic locomotion. Its speed and agility do not come from raw power alone but from a highly efficient combination of elastic tendons, lightweight bones, and finely tuned neuromuscular control. Engineers mimic these biological systems by using series elastic actuators that store and release energy much like tendons do. They model robot movements using spring-loaded inverted pendulum dynamics, allowing robots like the MIT Cheetah and Boston Dynamics Spot to run, jump, and maintain balance even on uneven terrain. These robots are capable of dynamic locomotion that was unthinkable using conventional rigid designs. Aerial robots have also taken inspiration from birds and insects. Birds constantly adjust their wing shapes to optimize lift and maneuverability, especially during takeoff, gliding, and landing. Insects, on the other hand, use rapid flapping motions with natural torsion in their wings to achieve incredible agility in tight spaces. Engineers have adapted these biological behaviors using morphing wing drones that rely on soft internal actuators, as well as flapping wing micro-air vehicles powered by piezoelectric artificial muscles. Computational fluid dynamics helps fine-tune these wing designs, allowing drones to fly in forests, collapsed buildings, and disaster zones where traditional quadcopters struggle. Nature also inspires advanced materials and structures. One of the most famous examples is gecko-adhesion. Geckos can climb vertical glass using millions of microscopic hairs on their feet, which create temporary van der Waals forces. Engineers replicate these structures by fabricating synthetic micro-hair materials that allow robots to climb smooth walls, inspect buildings, or perform maintenance in hard-to-reach places, even in space. Another example comes from the internal structure of bones. Bones are incredibly strong yet lightweight because of their internal lattice structure called trabecular bone. Using 3D printing and generative design, engineers mimic this natural lattice to create stronger and lighter robot frames, reducing weight without sacrificing stiffness. Soft materials also play a major role in bio-inspired robotics, especially materials inspired by marine life. Sea cucumbers can change their body stiffness almost instantly, and octopus arms move using muscle hydrostats that provide infinite degrees of freedom. These mechanisms lead to soft robotic actuators, variable stiffness grippers, and flexible robotic arms capable of moving safely around humans and navigating confined spaces. After structure comes actuation. Engineers have developed several bio-inspired actuators that function more like muscle than motor-driven systems. Pneumatic artificial muscles contract smoothly and naturally, producing high forces while remaining lightweight. Electroactive polymers deform when exposed to electric fields, allowing for soft artificial muscles that bend and stretch. Hydrogels respond to moisture, temperature, or electrical stimulus and can mimic the behavior of biological tissues. These actuators reduce the need for rigid joints and enable robots to handle delicate objects, adapt to unpredictable environments, and perform movements impossible with traditional rigid mechanisms.